Hello friends, welcome you all to the next lecture of JC eConnect series of online lectures. We have started with module 4 and we are dealing with the topic centroid. So in today's lecture we will be deriving the equations for centroid of various simple plane laminar figures and the basic steps to be followed to obtain those relationships are as given below. These are applicable to all the derivations. So if you are able to manage these 5 steps, the derivations will become a lot easier. So in the first step, we have to identify the figure and obtain its area. Say it's a rectangle or a semicircle or a quarter circle, and from our basic knowledge we have to find its area or the relationship for the area in the first step. Then in the next step we have to consider a small elemental strip from the entire area for analysis and obtain the area of that small elemental strip, which we'll name it as dA. Okay, now next in the third step, develop the equation to obtain the moment of that area, okay, moment of that elemental area with respect to the axis under consideration. That is, what is moment? Moment equal to dA, which is the small elemental area, into perpendicular distance with respect to the axis under consideration. That is the perpendicular distance of that small elemental area with respect to the axis under consideration. In the fourth step, use integration to find moment of all such elemental areas, because if we take the entire figure or the entire area, it will be made up of a number of such small elemental areas. So to find the moment of all the areas, we use integration within the well-defined upper limit and lower limit. Then next, in the fifth step, we use the principle of moments. What does the principle of moment say? The moment of all the elemental areas about any axis is equal to moment of entire area about the same axis. Okay, we use this principle to obtain the required relationship. So it's just a 5-step procedure, more of common sense and basics which you have studied at school level, and the derivations are very easy and very important from final exam point of view. Out of these 5 or 6 derivations which we will discuss, one is 99% sure in your final exams. Okay, so please make a note of these derivations and study them properly. So let's start with the first figure, which is a rectangle. So rectangle is a very common figure. Now the most important point to be noted here is rectangle is a symmetrical figure about both x as well as y axis. So actually there is no requirement of a derivation. Directly the center of the figure itself is the CG, which is located at half of the depth and half of the width. Okay, but still, for getting used to the further derivations, we will derive and prove it. So first step, we have identified the figure as rectangle, and the area of the rectangle is breadth into depth, that is B into D. That is capital A, that is the area, is equal to B into D. Next, we will consider a small elemental strip which has a depth of dy, breadth of B itself, and it is located at a distance y from AB. Now AB is the reference, or say AB is the axis about which we are going to locate the centroid of this figure. Now as the axis is horizontal, that is AB is horizontal, we will need to find y bar in this case. So if you want to try, you can take the axis as AD. In that case you will need to find x bar. So remember this, whatever is the axis under consideration, we will need to find the perpendicular distance as the centroidal distance. So in this case AB we are taking as a reference axis, about which all the moment needs to be calculated. Hence, our derivation will end when we obtain y bar. So, the moment of that small elemental strip about AB is area into distance, which is equal to B into dy is the area, and distance with respect to AB, that is the perpendicular distance, is y. Therefore, moment is B into dy into y. So, these are the first two basic steps which we have covered here. Further, some of such elemental strips now we have to take about AB. So now here comes the application of integration. So fixing the limits in integration is very important. So the lowermost limit what we'll get is what? 0. Okay, that is at level of AB. And the uppermost limit, which will be the CD. Okay, the uppermost limit will be D, that is the depth varies from 0 at AB, and at CD it's the maximum depth which we get is the small d. Hence our integration limits are 0 to D. Now what we have to integrate? The moment of the elementary strip, that is B into dy multiplied by y. So application of integration is very easy. As the variation is considered along the depth, B we will take it out, okay, because we are not applying integration with respect to B, we are applying integration with respect to D. Therefore, integrating we get moment of all the elemental areas about AB as BD square by 2. So this completes our fourth step. Okay, this completes our fourth step where we are able to obtain moment of all the elemental areas in the integration limit of 0 to D about the axis which we have selected, which is AB, or say horizontal axis in this case. So now last step is to apply principle of moments. What does principle of moments say? The moment of all the elemental strips of the area with respect to an axis is equal to the moment of entire area considered together with respect to the same axis. That is, we have to equate BD square by 2 is equal to B into D, which is the area of the entire figure, multiplied by y bar. Here y bar is the centroidal distance of the entire figure. Okay, so as I had stated earlier, our derivation will end when we find y bar. Therefore, cross multiplying we will get y bar is equal to D by 2. So I told that this is a symmetrical figure, hence y bar will be equal to D by 2 and x bar will be equal to B by 2 with respect to the base or with respect to the vertical sides. Okay, so this is a very easy derivation, and generally the derivation of rectangle is not asked, but I am putting it forth so that you will get the idea of those 5 steps which I mentioned earlier. So next we'll come to the derivation of centroid for a semicircle. Mark this, very important. Many times it has been asked in the question paper. In fact, in the previous university question paper itself, this derivation was asked. So now let us start with the derivation for centroid of a semicircle. So now we are taking semicircle such as its diametrical axis is along the vertical. Okay, its diametrical axis is along the vertical. In textbooks you might find that the diametrical axis is along the horizontal. Both ways you can do it. Okay, so let's start. So area of the semicircle is what? Pi r square by 2. First step. Next is we will take an elemental area. In this case it will be a triangular elemental area. Okay, so now your basics come into picture here. The arc length, okay, arc length is given by L is equal to R into theta, but in this case our triangle is subtending an angle of d theta. Therefore the arc length, which forms the base of our triangle, okay, which forms the base of our triangle, the arc length is given by r into d theta. Therefore, the base of our triangle is nothing but r into d theta. So, let's find the area of this elemental strip. Area of a triangle is given by half base into height, right? So, half our base we have found out to be r into d theta, and height is nothing but the radius of the semicircle itself. Therefore, we get the area of the elemental strip as what? Half into r d theta. Okay. So, this should be very much clear. Now, next comes the concept of application of centroid. Already we have derived the centroid for a triangle. That same application we are going to use here. From the base of the triangle, okay, from the base of the triangle, the centroid lies at what distance? If h is the height, h by 3. Okay, at h by 3 we will find the centroid of the triangle. Now, in this case, the height of the triangle is nothing but the radius r as shown in the figure which is there besides. So, for this particular case, our centroid from the base will lie at what distance? R by 3. Therefore, from the tip, that is from point O, okay, it will lie at what distance? 2r by 3. So, this is a very important thing. The centroidal distance of this triangular element with respect to the apex of the triangle is at a distance 2 by 3 into r. Okay, so note down this point, which is very important, as it is mentioned here in the video in the last line, 2 by 3 r from O. Now next, this distance is inclined, but to find the moment we require horizontal distance in this case. Okay, hence the horizontal projection of this distance is nothing but 2 by 3 r into cos theta. Always remember, for any inclined line, okay, or say hypotenuse of a triangle, if you want to find the horizontal projection, it is cos of the angle, okay, cos theta multiplied by length of that inclined line or the hypotenuse. Whereas if you want to find vertical projection, it will be sin theta. So here in this case we require horizontal projection, hence we get a horizontal projection as 2 by 3 r into cos theta. Now this 2 by 3 r cos theta will be the horizontal projected distance of the centroid of the element, okay, which we will be using to find the moment. Because what is our definition of the moment? Area into perpendicular distance. So here we have a reference axis as vertical diametrical axis. Hence our perpendicular distance should be horizontal, and that horizontal distance is 2 by 3 r cos theta. So this is the initial step, and this is very important. Understanding this, you can easily go ahead with the derivation. So now same thing in the next step, moment of the elementary strip about y-axis is what? Half into r d theta, that r and r is multiplied and made r square, multiplied by horizontal distance. So what was our horizontal distance? 2 by 3 r cos theta. Therefore we get the moment of that single triangle, okay, with respect to the vertical axis which is our reference, as r cube cos theta d theta divided by 3. So it's a bit tedious process. Concentrate and understand. If you don't get this, today itself contact me. Now fixing of the limits is the next step. So I have drawn a basic diagram besides, which represents the semicircle which we are considering. So the variations in this case are from what? In the above quadrant we have a variation from 0 to pi by 2. In the below quadrant we have a variation from 0 to say minus pi by 2. Okay, so entire is a semicircle, so pi by 2 to minus pi by 2, which will be 180 degrees, right? So we have fixed the upper limit as pi by 2, the lower limit as minus pi by 2. Now with this limit, what we have to integrate? The moment of single elemental area. So if we integrate with the limit, upper limit as pi by 2, lower limit as minus pi by 2, we will get the moment caused by all such elemental strips in that semicircle. Therefore, applying integration for r cube by 3 cos theta d theta with the lower limit of minus pi by 2 and the upper limit of pi by 2, we get the relationship as 2r cube by 3. Okay, so this is our fourth step. The output of our fourth step is 2r cube by 3. Then in the last step, we have to apply principle of moments. So moment of the total area is pi r square by 2, which is the area, into x bar. So now here what we are equating? 2r cube by 3 we are equating with pi r square by 2 into x bar. Therefore, equating 2r cube by 3 is equal to pi r square by 2 into x bar. Cross multiplying, we get x bar as 4r by 3 pi. That is the centroidal distance with vertical diametrical axis, that is x bar is equal to 4r by 3 pi. So now see here friends, the differences we considered here, the reference as vertical, hence we got answer in terms of horizontal, that is x bar. For the derivation of rectangle, our axis was horizontal, hence we got the output in terms of y bar. Okay, so that is the difference. Now if we apply the same things what we have done, but our semicircle is along which axis now? Horizontal diametrical axis. Okay, so in this case what we will get? Y bar is equal to same 4r by 3 pi. Now the good thing with the semicircle is it will be symmetrical about one axis. Okay, so if we are taking the semicircle as shown now in this figure here, what we are dealing with, okay, it was about which axis? Vertical axis. Okay, hence if we cut it horizontally, we will get top and bottom part same. Okay, now if you consider the next type of semicircle which I have drawn in the current view, this is about which axis? Horizontal diametrical axis. Okay, so if we cut it, left and right will be the same. Okay, so in this case, your x bar will get directly, which is equal to the radius. Okay, horizontal distance will get directly, we need to find y bar. Whereas in the previous case, y bar we get directly and we need to find x bar. So things are simple. Maybe you might get a bit confused initially, but follow those 5 steps and solve the examples, or solve the derivations. All the derivations move on the same exact principle. There is no variation in that. So now let's move to the last derivation for today, which is a quarter circle. Now the easy thing about this is quarter circle is half of the semicircle. Okay, so firstly area will reduce, that is instead of pi r square by 2, area what we will take here is pi r square by 4. All the procedure for this remains exactly the same. What changes? First changes area of the semicircle to area of the quarter circle, that is in this case the area of the figure will be pi r square by 4, and the limits change because for a quarter circle the limits will be from 0 to pi by 2. Okay, whereas for a semicircle we had taken limits for pi by 2 to minus pi by 2, that is 180 degrees, whereas a quarter circle covers only 90 degrees. Rest all process is exactly the same, only 2 changes. One is the area of the entire figure, here in this case it is pi r square by 4. Second change what we get is the limits, that is the limits are here from 0 to pi by 2. Only that is the change, entire derivation remains the same as it is. Okay, so just briefly we'll go through this derivation also. Again here we are considering an elemental triangular strip. Area of that strip will be half base into height, applying the same principle of arc length what we applied previously. Area will be half r into r d theta. Now remember here, as we are taking that elemental strip, we are not taking the curvature into account. Okay, the arc length we are considering it as flat base of the triangle. Don't worry or don't think that as it is curved, how we are taking it as a triangle. These all are basic assumptions. Okay, need not worry about it. So next step, again the horizontal projection of that will be same, 2 by 3 r cos theta. Don't worry much. Okay, horizontal projection will be always 2/3 r cos theta. Okay, so cos theta gives the horizontal projection in any and every case. So next, finding the moment of the elementary strip about the y-axis, it goes exactly the same, need not worry. Now the difference here is when we take integration, limits will be now 0 to pi by 2, whereas in previous case our limits were different. Okay, so this point is very important. Just see the integration limits. So once we integrate, we get r cube by 3. Okay, this is what r cube by 3 is, moment of various triangular strips in that quarter circle with respect to the axis under consideration. Next, moment of the total area is total area pi r square by 4. So here is a variation, it is r square by 4, pi r square by 4, because it's a semicircle, into x bar, because we are locating the CG with respect to vertical axis. Okay, hence it is x bar. Therefore now we have to equate what? R cube by 3 is equal to pi r square by 4 into x bar. So doing that, we get the answer again as 4r by 3 pi. Okay, 4r by 3 pi. Similarly, we can prove that y bar is equal to 4r by 3 pi. So when we consider a quarter circle, it is neither symmetrical about x-axis nor it is symmetrical about y-axis. Okay, hence we get formula for both x bar as well as y bar. So now in today's examples, if we consider, first figure was a rectangle. Okay, it was symmetrical about both the axes. Then we took a semicircle. Okay, depending on the orientation of the semicircle, either it will be symmetrical about x-axis or y-axis. Now in the third case, we have taken a quarter circle. Okay, quarter circle taken in any quarter won't be symmetrical about any axis. That means you need to find both x bar as well as y bar. Okay, so in this derivation it is important to write this step. Similarly, we can prove y bar is equal to 4r by 3 pi. Okay, so understand these derivations, go by the basic 5 steps which have been explained in the first part of the video. Okay, write these derivations which are easy, follow those principles. If you have any doubts, please get back. Next video will be uploaded, in which we will be having a derivation for sector and the list of formulas, and then further we will be starting with the examples. So hope you are keeping the notes up to date, and from now on we will have civil lectures continuously. Thank you. Have a nice day.